now? Yeah, I don't think there is a graph. So question 20. Which of the following reactions would increasing pressure at constant temperature change the concentration of reactants and products based on Le Chatelier's principle? Yeah, Chris, we'll get there in a second and we can talk about it. Yeah. So basically, if we increase pressure on a reaction, it can influence the equilibrium if there are unequal number of moles on both sides of the reaction. So the one trick in this question is that they're not asking for a direction. They're not saying to the left or to the right. They're just saying, in which case will the concentrations of products and reactants change? So basically, we're looking for all cases where the number of moles on each side is different, because if the moles are different, then pressure will have an influence on equilibrium. So here I've got 4 versus 2. So that one works. I've got 1 versus 2. That one can also be influenced by pressure. I've got 3 versus 2. That can be influenced by pressure. And I've got 3 versus 2. That can be influenced by pressure. So E, all of the above, all of those reactions can be influenced by pressure because they have a different number of moles in the gas phase on both sides of the reaction equilibrium. For question 21, Kc of the equilibrium is that. Oh, okay, what is the value of Kc at the temperature of the following reactions? So they tell us that Kc in the first reaction, so Kc1 equals 7.52 e to the negative 2. So to go from the first reaction to the second reaction, we have to do 2 operations, right? Choice E, Haley, all of the above. So between these 2 reactions, we actually do 2 things to that reaction. We flip the reaction, which is the same as taking the inverse of my equilibrium constant. So Kc1, Kc2. So that's the first one. If we flip the reaction, we do the inverse of the equilibrium constant. The other thing we should notice is that I multiplied the reaction by 2. Multiplying the reaction by 2 is the same as squaring the equilibrium constant. So my new equilibrium constant is going to equal 1 over my initial equilibrium constant squared for question 21. So I get choice 1. I get an equilibrium constant of about 177. So yeah, 1.77 e to the 2 for that. Question 21. I think someone asked for question 22. If not, it's a super easy question, so we can go through that quickly, right? How many transition states and intermediates do we have? So transition states, right, are the peaks. So there are 3 transition states, and intermediates are the valleys that are in between. So I have 2 of those. So 3 transition states and 2 intermediates. So let's see. It looks like choice D here. 3 transition states and 2 intermediates for 22. Question 23 is a little bit tricky in that reaction coordinate diagrams can go left to right or right to left. We can take the reaction either way because all these reactions are reversible. So using the reaction coordinate diagram, which would be the slowest step of the reaction, the slowest step of the reaction is the highest activation energy, the highest hill in that reaction. The steepest hill in that reaction is the slowest step. It's going to take a lot more energy to get to the top. So the slowest step of this reaction is actually in the reverse direction, right? From G going to F is the slowest step in the reaction. So that's choice D for question 23. All right. Now question 24, which maybe that's down here. Oh, okay. So yeah, Chris, question 25 should look like that. You should have a table like that. We can figure out what's going on if you don't for some reason. But question 24. This is similar to the other half. All right. This is similar to the other half of the other half-life problem that we did. So question 24, it's an important radioactive isotope that's used to enhance the medical imaging. They give us the rate constant of the reaction, right? Here's our rate constant. Yeah, we're doing 24 right now. They give us the rate constant of the reaction. They tell us it's first order. And they want us to find out how long it's going to take for all the technetium to break down to 1% of the original sample. So now we don't have a nice half-life number. Now we have to do the integrated rate law for a first order reaction because we know it's a first order decomposition, right? Or first order decay. So natural log of concentration at time t equals negative kt plus the natural log of time 0. So A at time 0, because we're looking for a percentage, we're going to say A at time 0 is 100%. So in decimal form, right, we're just going to use 1. At time 0, I have 1. And then at some point in the future, I have 1%. So A at time t, I have 1%, which is 0.01 in decimal format. And I'm going to have to plug in my computer in a second here. So we plug all that in, right? Natural log of 0.01 equals negative rate constant 1.925 e to the negative 3 minutes. My time is in minutes, and that's going to be plus the natural log of 1. The nice thing about this is the natural log of 1 is 0. So that makes our equation a lot easier. Basically, the natural log of 0.01 is a negative 4.605 equals negative 1.925 e to the negative 3 inverse minutes times time. Divide both sides by a negative 1.925 e to the negative 3. And I get time for this reaction, 4 significant figures. So 2,392 minutes. So 2.392 e to the 3 minutes for that reaction. All right, any questions on 24?